So let's talk about something that sounds like it's straight out of science fiction, but is very, very real: quantum computing. Now, this isn't just about making faster computers. This is a technology that could totally redefine the limits of what's possible. But, and this is a big but, it also holds a pretty serious threat. It could potentially shatter the foundations of our entire digital world, laying bare every secret we've ever sent online. We're going to explore how this new era is dawning and what it really means for, well, everything.
I mean, really think about it for a second. Everything you do online, sending a private message, typing in your credit card number, logging into your bank account, we trust that it's all secure. But what if the lock protecting all of that has a fundamental flaw? And what if people are already recording our encrypted data, just waiting for the day they can build the right key to unlock it all? It's a strategy called harvest now, decrypt later, and it makes the threat of quantum computing a very real problem for today, not some far-off future. Okay, so to really get why this is such a huge deal, we first have to understand the lock itself. How are we protecting all this digital information? Well, it's not with a physical vault or some super complex password. The security of the entire modern internet rests on a single, beautifully elegant, and incredibly hard math problem. Right. Here's the core idea. We've built our digital world on a mathematical puzzle that is, for all intents and purposes, impossible for the computers we have right now to solve. Think of it like a one-way street. It's super easy to create the lock, but it's nearly impossible to go backward and figure out the key. This whole concept is the bedrock of what we call public key cryptography. The most common system you'll see out there is called RSA, and its strength, its power, it all comes down to one specific task: factoring. Now, we all learned in school that the factors of, say, 15 are 3 and 5. Easy enough, right? But what if I asked you for the factors of a number that's 600 digits long? Yeah, that's a completely different beast. And that difficulty is the very heart of RSA security. So let's break down how this actually works. Picture your bank server. It secretly picks two absolutely massive prime numbers. Then, it multiplies them together to create an even more enormous number. That number becomes the public key. Your web browser uses that public key to lock up your data before sending it. But, and this is the critical part, to unlock that data, you need to know those two original prime numbers, the secret keys. And trying to figure out those original primes just by looking at the public product, that's the math problem that just completely stumps every conventional computer on the planet. And when I say it stumps them, I'm not kidding. We're not just talking about your laptop. We're talking about the most powerful supercomputers on Earth. For a standard run-of-the-mill 2048-bit key, one of these supercomputers would need to run for longer than the age of the universe to find the factors. So yeah, this lock is, for all intents and purposes, unbreakable. At least by the computers we've always known. But what if? What if we built a new kind of computer, one that just doesn't play by the same rules at all? This new machine is built on a totally different component, the qubit. It's the quantum world's answer to the classical bit, but it comes with some very, very strange and powerful new abilities. A classical bit, that's simple. It's a light switch. It's either off, which is a 0, or it's on, which is a 1. That's it. A qubit, though, a qubit is more like a dimmer switch. It can be 0, it can be 1, or it can be in some state that's a combination of both 0 and 1, all at the same time. This absolutely mind-bending property is called superposition. Probably the best way to wrap your head around superposition is to think of a spinning coin. Well, it's up in the air, just spinning away. Is it heads or is it tails? Well, in a way, it's both. It only picks one definite state, heads or tails, when it finally lands and you look at it, when you measure it. A qubit is just like that spinning coin. It exists in this fuzzy, probabilistic cloud of both 0 and 1, and only snaps into one state when we measure it. And this is where things get wild. Because a single qubit can represent both 0 and 1, a system of qubits can hold an exponential number of values at the same time. I mean, a system with just 300 or so qubits could represent more possible states than there are atoms in the entire known universe. It gives a quantum computer this almost unimaginable power for parallel processing. And as if superposition wasn't weird enough, qubits have another trick up their sleeve. It's a property so bizarre that it famously freaked out one of the greatest minds in physics, Albert Einstein, and it gave us one of the most famous phrases in all of science. That's what Einstein called it: spooky action at a distance. He just could not get on board with the idea that two particles could be linked in this way, where they could seem to influence each other instantly, no matter how far apart they were. But, as it turns out, the universe is just that spooky. So what entanglement is, it's this deep, unbreakable connection between qubits. Imagine you have two of those spinning coins from before, but this time they're entangled. If one of them lands on heads, you instantly know, I mean instantly, the other one has landed on tails. And this holds true whether they're sitting next to each other in a lab or they're on opposite sides of the galaxy. Their fates are linked. It's not communication, but it is a powerful connection that gives quantum computers another one of their superpowers.
So we have these two incredible properties: superposition, which allows for this massive parallelism, and entanglement, which creates these spooky connections. Now we get to the heart of the story. How do these bizarre quantum effects combine to create the master key for our so-called unbreakable digital locks?
This is the multi-trillion-dollar question, right? A classical computer, it attacks the RSA lock with brute force. It's just trying one possibility after another after another. It's like trying to open a door by using every single key that exists on the planet, one by one. A quantum computer, it takes a fundamentally different and way, way smarter approach. The answer lies in a specific recipe, a special set of instructions called Shor's algorithm. Now, what this algorithm does is it basically turns the factoring problem into a hunt for a hidden pattern, like finding a secret rhythm in a huge jumble of noise. It uses superposition to look at all the possibilities at once. Then, through this amazing process of quantum interference, it makes all the wrong answers cancel each other out, while making the signal of the right answer stronger and stronger, until it's the only one left.
The power of this is it's hard to overstate. A problem that is effectively impossible for a classical supercomputer becomes trivial for a powerful enough quantum computer. The digital lock that would take billions of years to pick could be opened in a matter of hours, or maybe even minutes. I mean, let that sink in. Every encrypted email, every secure transaction, every government secret, just wide open. But, and this is a huge but, it's not all doom and gloom. Breaking codes is really only one side of the quantum story. This technology isn't just a weapon for destruction, it's also an incredible tool for creation. The exact same properties that threaten our security also make it a revolutionary engine for science and innovation, opening up frontiers we've only dreamed of. I'm talking about things like simulating molecules with perfect accuracy to design new life-saving drugs, or picture creating brand new materials with unbelievable properties, like superconductors that work at room temperature. These machines could completely change financial modeling to help us predict market crashes, or they could supercharge AI and machine learning. The potential is just vast. So, should you be panicking? Is the internet about to break tomorrow? Well, the short answer is no. We are in what experts call the NISQ era. NISQ stands for Noisy Intermediate Scale Quantum. Basically, today's quantum computers are amazing, but they're still noisy, meaning they're really sensitive and prone to errors, and they're intermediate scale, meaning they don't have enough high-quality qubits to run something like Shor's algorithm effectively. So the threat isn't immediate, but it is definitely on the horizon, and the race to get ready has already started. And that brings us to the final crucial point. We are standing at a major technological crossroads. Down one path, there's this unprecedented computational power for good. And down the other, a cryptographic apocalypse. The good news is, scientists are already developing what's called post-quantum cryptography, new ways to encrypt things that are safe from both classical and quantum computers. The real question is how we navigate this transition. How do we harness the incredible promise of this technology while protecting our digital world from that very same power? The race is on.